You can't see the future. That's so obvious it barely sounds like a statement worth making. Of course you can't. Nobody can. The future hasn't happened yet. That's what makes it the future. But here's the thing. The laws of physics don't agree with you. Write down Newton's laws of motion. Write down Maxwell's equations for electromagnetism. Write down Schrödinger's equation for quantum mechanics. Einstein's field equations for gravity. Take any of them, any of the fundamental equations that govern how the universe works, and run them backward in time. They work perfectly. The physics is symmetric. There is no arrow of time in the fundamental laws, no label that says past points this way, future points that way. The equations that describe every particle, every field, every interaction in the known universe treat time as completely reversible. And yet here you are, unable to remember tomorrow, unable to undo yesterday, experiencing time as the most one-directional thing there is. Something has gone profoundly wrong between the equations and the experience. That gap between time-symmetric physics and the one-way time you live in is one of the deepest unsolved problems in all of science. Let me be precise about what time reversal symmetry actually means, because it's easy to misunderstand. It doesn't mean the universe looks the same running backward as forward. It means if you take any physical process and reverse it, run the movie backward, the reversed process is also a valid physical process, one that the laws permit. A ball rolling across a frictionless surface and stopping isn't time-symmetric because of friction. That's dissipation, which is thermodynamics, which we'll get to. But a ball rolling across a truly frictionless surface? Reverse it. Still valid. An electron orbiting a nucleus? Reverse the trajectory. Still valid. Two particles colliding elastically? Reverse all the momenta. Still valid. At the level of fundamental particles and their interactions, the laws are symmetric under time reversal. The microscopic world doesn't have a preferred direction baked into it. There is one small exception worth mentioning: CP violation in weak nuclear interactions, a tiny asymmetry between matter and antimatter that has a time reversal implication through a theorem called CPT symmetry. It's real, it's been measured, and it is far, far too small and specific to account for the massive, overwhelming time asymmetry of the macroscopic world. The coffee cooling in your cup, the smoke spreading through a room, the egg that doesn't unbreak. Those irreversibilities don't come from CP violation. They come from somewhere else entirely. The second law of thermodynamics. In a closed system, entropy tends to increase. Entropy is a measure of the number of microscopic arrangements, microstates, that are consistent with the macroscopic state you observe. High entropy means many possible arrangements. Low entropy means few. A hot gas confined to one corner of a box has low entropy. The molecules are all in one place, a very specific macroscopic configuration. Let it spread. Now the molecules are distributed throughout the box, many more possible arrangements consistent with that macroscopic state, high entropy. The process runs in one direction, not because the laws forbid the reversal, but because the reversal is astronomically improbable. The number of microstates in which all the gas happens to be back in one corner spontaneously is so vanishingly small compared to the number of spread out configurations that you will never see it happen. Not in the lifetime of the universe, not in 1 trillion times the lifetime of the universe. The arrow of time is statistical. It points toward higher entropy not because the physics demands it, but because the probability weight is so overwhelming that toward higher entropy and toward the future are, for all practical purposes, the same direction. This is the mechanism behind every irreversible process you've ever witnessed: the broken egg, the melting ice, the irreversible decisions. All of them are the universe moving from lower to higher entropy, not because it must, but because high entropy states vastly outnumber low entropy states, and random dynamics will almost always move you toward the more probable. But this explanation immediately creates a serious problem. If entropy increases toward the future because high entropy states are more probable, why doesn't entropy also increase toward the past? Think about it carefully. If you have a system in a low entropy state right now, the statistical argument says it will move toward higher entropy in the future. But the same argument, run backward, says it probably came from higher entropy in the past. A low entropy present is statistically unlikely to have come from a lower entropy past. So if entropy is just statistics, the most probable history for any low entropy state is that it fluctuated down from a higher entropy past, not that it descended from an even lower entropy one. But that's not what we observe. We observe that entropy has been increasing consistently in one direction for 13.8 billion years. The past is systematically lower entropy than the present, and the only way to make the statistical argument for the arrow of time work is to assume, without deriving it, that the universe started in an extraordinarily low entropy initial state. Physicist David Albert calls this the past hypothesis. It's not a theorem, it's an assumption. We simply posit that the Big Bang was a highly ordered, low entropy event, and everything since has been the universe spreading into more probable configurations. This works. It gives us the arrow of time. But it immediately raises the question you cannot ignore. Why did the universe start in such an improbably ordered state? The Big Bang as it occurred, smooth, homogeneous, hot, dense, is in fact a very low entropy configuration. Roger Penrose has estimated the probability of that specific initial state among all possible initial states of similar energy as roughly 1 in 10 to the power of 10 to the power of 123. That's not a small number expressed poetically. That's a specific estimate of how cosmically improbable the initial conditions were. We don't know why those initial conditions existed. We don't have a theory that selects them. The arrow of time you experience every moment of your conscious life traces back to an unexplained fact about the first moment of the universe. Now bring in quantum mechanics, because it adds something new and it makes the question harder. Between measurements, a quantum system evolves according to the Schrödinger equation. That equation is, like all the others, perfectly time-symmetric, deterministic, reversible. A quantum state spreads as a wave function, and you can run the evolution forward or backward, and it works equally well. But when a measurement is made, when a quantum system interacts with a measuring device or an observer or any macroscopic system large enough to count as classical, something different happens. The wave function, which described a superposition of many possible outcomes, collapses to a single definite result. This collapse is not time-symmetric. It selects one outcome and discards the others. It's irreversible. This introduces a different kind of future blindness. Not just hidden information, genuinely undetermined outcome. Before you measure the spin of an electron, it doesn't have a definite spin. Not that you don't know it, not that it's hidden from you. In the standard interpretation of quantum mechanics, there is no fact of the matter until the measurement occurs. The future, at the quantum level, isn't just unknown to you. In at least some interpretations, it simply doesn't exist as a definite fact until something interacts with it and makes it real. This is the measurement problem, and it's unsolved. Whether wave function collapse is a real physical process, something that objectively happens in the world, or an artifact of decoherence and the way large systems interact, remains one of the most contested questions in foundations of physics. Different interpretations of quantum mechanics give radically different answers. Many worlds says the collapse is apparent. All outcomes happen in branching realities. Copenhagen says the collapse is real, but doesn't ask what mechanism produces it. Pilot wave theory says the particle always had a definite position. We just couldn't know it. Each interpretation gives a different answer to the question of whether the future exists. Not a different description of the same physics, a different ontology, a different claim about what's real. Here it's worth separating two things that often get conflated, because confusing them leads to real confusion about the nature of time. There's the question of whether you can predict the future, and there's the question of whether the future exists. Classical chaos is about predictability. The weather system is, if you believe classical physics, deterministic. Every raindrop follows Newton's laws exactly. There's a fact of the matter about whether it will rain on a specific Tuesday 3 months from now. But the system is so sensitive to initial conditions, the classic butterfly effect, that tiny errors in measurement amplify exponentially. A small uncertainty about today's atmospheric state becomes a large uncertainty about next week's. Prediction becomes practically impossible beyond a week or so. This is epistemological unpredictability. The future exists. It's just inaccessible to computation from where you are, with the precision you can achieve. Quantum indeterminacy is different. The electron's position before measurement isn't just unknown, it may be genuinely undetermined. This is ontological, not a question about what you can know, but a question about what exists. The line between those two is one of the most contested in physics and philosophy. Whether quantum mechanics is telling us about the limits of knowledge or about the limits of what's real depends on which interpretation you adopt. And no experiment so far has been able to distinguish them. Now I want to take you somewhere that most discussions of this topic don't go, because there's a picture of time that comes from relativity, and it's in direct tension with everything I've just said about quantum mechanics, and both are supported by well-tested physics. Special relativity showed something radical. The distinction between past, present, and future is not a global, observer-independent fact. Two observers moving relative to each other will disagree about whether two events are simultaneous. There is no universal now that all observers share. What's in your present is not in the present of someone moving past you at high velocity. The philosophical implication that many physicists and philosophers draw from this is called the block universe, or eternalism. If there's no privileged now, no special moving present moment that separates what exists from what doesn't, then perhaps all moments of time exist equally. Past events, present events, future events, all of them are equally real parts of a four-dimensional space-time. The future isn't something that hasn't happened yet, it's something you haven't reached yet. In this picture, you can't see the future not because it's undetermined, but because of your causal structure, the light cone of what information can have reached you given the speed of light. The future is real, it's causally inaccessible. And now you see the tension. Quantum mechanics, at least in its standard interpretation, says the future is genuinely indeterminate, not yet real, created by the process of measurement or interaction. Relativity says the future is already there, in the block, equally real as the past. Both theories are spectacularly successful. Both make predictions confirmed to extraordinary precision. And they're telling contradictory stories about whether the future exists. Reconciling them is the project of quantum gravity, a theory we don't yet have. There's one last layer, and it's the one that brings this question closest to home. All the physics I've described, low-entropy initial conditions, entropy increase, quantum decoherence, relativistic causal structure, explains why macroscopic processes are irreversible, why broken eggs don't reassemble, why heat flows one way, why information spreads. But it doesn't explain why you feel time moving forward. The brain encodes memories of the past. It has no memories of the future. This is thermodynamics, Recording a memory is a physical process that increases entropy, that writes information into a low-entropy physical system. Memory formation runs with a thermodynamic arrow because it's a thermodynamic process. But the subjective experience of time passing, the sense that now is moving, that the present is vivid and real in a way the past and future aren't, that time flows, that's not explained by entropy. It's part of the hard problem of consciousness applied to time. Why does a physical arrow of entropy produce a felt arrow of experience? Why is there a now at all? Dirac trusted mathematical structure more than intuition, and the mathematical structure of time is genuinely ambiguous in a way that should be unsettling. Symmetric at the fundamental level, statistical at the thermodynamic level, observer-dependent in relativity, indeterminate in quantum mechanics, and subjectively directional in a way none of the above fully accounts for. You can't see the future because the universe started in an improbably ordered state 13.8 billion years ago, and entropy has been increasing ever since. Because quantum mechanics may make the future genuinely non-existent as fact until it occurs. Because relativistic causal structure limits what information can reach you. And because your mind is a physical system that runs its records in one direction, with the arrow, and has no physical mechanism for the other. All of these are true. None of them is the complete answer. Time remains the thing you're most inside of and understand least. The equations don't have an arrow, you do. And the gap between those two facts is where some of the most important physics of the next century is going to be written.